Hi friends, welcome to a new, long overdue episode of Calculuscious Explains It All. With me, Calculuscious, aka Mathy Cathy, also known in the Math Excel world as Professor Shawley. I'm feeling very professorial today, but only because I'm wearing a sweater with elbow pads. See? Okay. It's been a long time since we've had one of these episodes, so let me remind you that this is the series where I claim to explain it all. Some might say that I explain nothing at all, and that would be fair. But I like to think of it as explaining just enough of something mathy to hopefully pique your interest and make you want to know more. In this episode, we are going to talk about derivative applications. Now, I have to confess that this video is much later in the school year than it should be. And if you know anything about math teachers, you know that we always feel that we are behind in the curriculum, but this year it is for real. I am way behind. But you know what? If 2020 has taught me anything, it is to be patient and take things as they come. So believe it or not, this year I am a math teacher that is not worried about being behind. I do want to apologize, though, to the people who were actually waiting for me to come out with new video lessons on derivative applications. I promise you they're coming, and I very much appreciate the messages from you that keep me motivated to do videos like this. All right, so at the end of our derivatives unit, I posted an assignment called Stupid Question Session. I actually do this. I started this year off of the recommendation of a retired math teacher. And it's been a wonderful little assignment where I asked students to post stupid questions that they have about the unit that we just covered or just about math in general. And at the end of our derivatives unit, this is the question I got most frequently. What's a derivative? And although it hurts a little bit because we've been talking about derivatives so much this year, it is a valid question. And I think students would be surprised to learn how many of them actually question their knowledge and understanding of derivative after an entire year of calculus. And that's because there's just so much going on in the derivatives unit to learn that sort of the concept of a derivative gets lost in all of the bits and pieces of rules and formulas and algebra and trig that you need to know. Now, if you've seen any of my episodes in the past, you'll know that I am mildly obsessed with Stephen Strogatz. And one of the reasons I am is because most things that I think at some point in my career, he confirms for me beautifully in his writing. So this New York Times piece that he wrote a long time ago, 10 or 11 years ago, I guess it would be, is an article that I use every year at the start of my applications unit to sort of get students in the mindset to be thinking more about the concept of a derivative and how it can actually be applied to real life scenarios. And in this article, he also, sorry, a little technical difficulty there. He also acknowledges that millions of students take calculus and they can't tell you what they are actually learning. And notice right here, he says it's not their fault. There's so many techniques to master. There's so many different things to have to keep track of that you miss the overall big picture. And that's actually why I often advocate for students to retake calculus in college, even if they've taken it in high school, because you get to sit back and see the bigger picture and absorb the concepts rather than just the procedures the second time around. Okay, so I'm not going to read any more of this article to you, but I will advocate that you take a look at it for yourself because, again, it is a really good starting point to understanding applications of derivatives. Now, these are the applications of derivatives that we typically look at in AP Calculus. We look at things like linearization, optimization, curve sketching, differentials, motion and rates of change is actually something that I already did some videos on, and finally related rates. And I'm going to just touch on each of these today very briefly to sort of hopefully give you an overall picture of what an applications of derivatives unit would look like as you study calculus. But first, if you don't mind, I might go on a little rant about this meme. Another day has passed and I still haven't used y equals mx plus b. Okay, Davry, or Davry, however you say it, you know I can't pronounce things. I understand what you're saying there, and I am a proponent of there being more courses in high school that are required that students feel could be useful to their lives. But I really don't think you should have picked y equals mx plus b to prove your point, okay? And also, I'm going to put this on you a little bit. You haven't found places where y equals mx plus b is useful. It's a little bit on you. There are plenty of places out there where it can be used, and I don't think you've looked hard enough in trying to find them. Like this. Okay, this is not the best example to start with, but I think it's pretty cool myself. So do you know how to take the square root of 123 by hand? Like, do you know how to just calculate the square root of 123? Like the steps you take? Okay, I'm going to tell you, I don't either. I tried to teach myself a long time ago, and I gave up because it was crazy. Taking a square root by hand is crazy. But I'm going to tell you something pretty cool right now. This little y equals mx plus b equation pretty much will do what you need it to do to calculate the square root of 123 by hand. Or better yet, so that we don't have to grab the calculator, let's go to a different version of this linear equation. Okay, so I'm going to write this equation in point slope form, in a particular point slope form, like this. And I don't expect you to really know where I'm getting these numbers from just yet, but I will explain. There we go. Okay, so the point slope form that linear equation that we can use to calculate the square root of 123 is y minus 11 equals 1 over 22 times x minus 121. And what you may notice here is that we have a number that is close to 123, and it is a perfect square, right? We know that the square root of 121 is 11. That is called a center of approximation. And in this point slope form, we would call that x1, y1. Where is the 1 over 22 coming from? Well, that's the slope, right? How do we calculate that slope? We look at our square root function. We take its derivative. Remember, the square root of x is x to the 1/2, so this is 1/2 x to the negative 1/2 power. And then we sub in the x value from the center of approximation. And that is how we get a slope of 1 over 22. Now, if we take this point slope linear equation and we sub 123 in for this x, you might as well say you are taking the square root of 123. Because doing the calculations needed here to solve for y is going to give you the square root of 123, accurate to the nearest tenth at least. So let's see, what's that? That's 2. 2 times 1 over 22 is 1/11th. Add the 11 over, and we got 11 and 1/11th. That's approximately what the square root of 123 is. Let's double check it with the calculator now. We'll grab the calculator and see how good we were. Okay, first let's do the square root of 123. Okay, next let's do what is that, 122 over 11 as an improper fraction. Look at how close we are. Oh my gosh, to the thousandths place close. Yay, we did it. And that is called linearization. What we just did was we took, let's see if I still have it in my calculator. I do not, but I can bring it up again. We took the square root of x, and we centered at this ordered pair, 121, 11. So I'm going to have to change my window a little bit here. Let's make the x max go all the way to 130. Let's make the y max go to 20. And, maybe we should change this to, I don't know, 25s. We'll see if that looks good. Okay, and now I'm going to get close to my center, and then I'm going to try to zoom in. I hope that when I hit this thing, okay, it's going to put me where I need to be. Oops, I don't want to do that. I want to zoom to, enter. And look at that. When you zoom in just once to the square root curve on this graphing calculator, you see it turn into a line, right? And the linear equation that I was referring to here, whether it be in this form or this form, that's the equation of this line. And the equation of this line can be used to calculate the values of other points that we don't know along the square root function's curve easily. So again, maybe that's not the best real life application of y equals mx plus b or derivatives, but I like to start with that one because I think it's kind of fun. Whenever I teach this, I usually have my students just guesstimate a square root, and then I show them how they can easily write the equation of a tangent line to accurately approximate a square root. And this has a lot of other implications as you continue on. You'll study higher degree approximations. This will then lead into Taylor series and Maclaurin series. And I think any physicist will tell you that those come in clutch. So this is just the beginning of something that's a really cool application of derivatives. Now let's talk about another really cool application of derivatives, optimization. Okay, so I have a prop for this. I have in my hand a box. It's a really pretty box, right? But it is a special box, not only because of how beautiful it is, but also because it is an open top box of maximum volume. Meaning, if I started with I believe this one was a square. It was like a 12 by 12 inch square. If I started with a 12 by 12 inch sheet of cardboard, and I want to turn it into an open top box that will hold as much as possible, okay, the maximum volume, then this would do it. These are the dimensions of the box that would do it. Now, how did my student figure out the dimensions of this beautiful box to hold the most candy for me, or whatever it is that we want to put in here? Well, she used calculus. She used derivatives. Okay. Oh, and I have a whole bunch of these, by the way. You want to see them all? I even have a giant one. I don't even think I can fit it over here right now. Yeah, look at that. I have a giant one because I let my students last year make their box be any size they want, and it just had to maximize volume given, whatever size they started with. Okay, so let's say, for example, that you start with some sort of rectangular sheet that is, let's say, 25 inches by 20 inches. And again, what you want to do is cut out corners here, 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 and here, so that you can then fold up the sides to make your open top box. What will the dimensions be of the little squares that you cut out to maximize the volume? That's actually what we're trying to figure out here. If you make the dimensions of those squares x, then you can easily write a volume function of your box. Given that the length would be 25 minus 2x, the width would be 20 minus 2x, and the height would be x. And from there, okay, what do we do? Well, we want to find the maximum point of this function, the maximum x value of this function. How do we do that? Well, I mean, okay, yeah, you could graph it if you have a graphing calculator and just find the highest point. But that's not fun. And also, it's not actually a very efficient method given certain constraints. So a better thing to do would be to find the derivative of this function, set that derivative equal to 0, and solve through what we call critical points. We can then test critical points to determine if a critical point is a maximum or a minimum value by looking at the signs of the derivative on either side of the critical point. Okay, I'm not going to go through this full example right now. This is just a preview for something that I will show you in my optimization video lesson, and you can look forward to that. Okay, but again, this is another place where derivatives lend a hand, and I think it's a really fun application, and also it is a very real-world application of derivatives. This has a lot of good applications that you could take into economics, you could take into product design, and we have a lot of fun with this application when we get to it in my class. At least I have fun. I don't know if they have fun. But look, it looks like they have fun, right? All right. Next, let's talk about another application, and this is referring to the signs of derivatives that I was just talking about previously, that I really like. I don't know, how real-world application it is. Sorry, Davery, or whatever your name was, but I'm going to go here anyway. This is called curve sketching. Curve sketching is where you take information about the derivative of a function to sketch the original function's curve. And I love this stuff. Give me some information about the derivative, ask me to sketch a possible curve of the function, and that just sounds like hours of fun to me. I don't know about you. Okay, and here's just one really simple example. So as I said, wherever your derivative is equal to 0, you call those critical points. And you can test critical points. You can test, I should say, the signs of the derivative around the critical points to determine whether a critical point ends up being a maximum point or a minimum point. Okay, maximums and minimums of a function occur where a derivative is equal to 0, or if you would ever have any endpoints of your function, those could always be maxes and mins as well. Also, it is important to note that critical points could also be where the derivative does not exist. Okay, we don't have any of those here. Okay, so here's how we can determine if a critical point is a maximum or a minimum. If your function's derivative is positive to the left of your critical point and negative to the right, think about what that means. That's saying slope is positive or increasing on this side. This would be a turning point, and then slope is negative. So that turning point or critical point would result in a maximum. And it's actually always that case, that if around a critical point your derivative is positive on the left and negative on the right, then what you have at that critical point is a maximum. On the other side, here we have the derivative being negative to the left of this critical point and positive to the right. So our function is decreasing, negative slope, decreasing on the left, then increasing on the right. That means that this critical point is a minimum. Okay, so what that does for our ability to curve sketch is it sets some points for us. When x is -2, I know that I have a maximum. I don't know exactly the function's value when x is -2, so I'm just going to sort of put it wherever I want. But I do know that that's going to be a relative max at least, meaning is the highest point in that region. When x is 1, I know that's a minimum. So again, I don't exactly know where that's occurring, but when x is 1, I can set a point and say that's going to be the lowest point in that region. Okay, I now know that my function is going up to this point, down to this point, and back up. So I can sort of get a rough sketch of what my graph should look like. It should look like that. Okay, but there's curving to it, right? We don't know the curving unless we look at some information about the second derivative, or we call this the concavity. This is looking at the concavity of our function. When the second derivative is negative, that means that our function is concave down. Down like a frown, okay? Oh, concave down again right here. When the second derivative is positive, we call that concave up, U for up. And that happens through here. When the second derivative is 0, that is not a max or a min, not necessarily. It is what we call a point of inflection, and that just means a point where the concavity changes. Knowing that term, though, can be helpful in other areas like economics. Point of inflection is where your concavity changes. Okay, so now what I know is that my curving should be down like a frown until x equals 0, and then U for up. So I am going to erase these lines. Oh, I guess I got to get rid of that, sorry. And I can curve my graph like this. Concave down to that point, and then it changes to concave up. Okay, and that's just a really simple mini example of what we call curve sketching, which again is something that you will most likely study when you look at applications of derivatives. Now, let's talk about differentials. Differentials is a way to use a derivative to approximate change, which again goes back to the fact that a derivative is a way to find a slope of a curve. A slope is a rate of change between two quantities, right? So when we write a derivative as dy over dx, this is saying the change of the y with respect to the change of the x. Now keep in mind that this is a limit as the change in the x is very small or goes to 0. And so that's why differentials is a way to approximate the change. It does not actually calculate true change. Okay, so let's take a look at this example, which is an example of a problem where we would use differentials. Suppose the Earth were a perfect sphere and we determined its radius to be 3,959 plus or minus a tenth miles. What effect would the tolerance of minus a tenth have on our estimate of the Earth's surface area? Okay, I don't think it's really apparent where derivatives are going to come into this problem. But let's just go ahead and do a derivative of the surface area formula of a sphere and see what happens. Okay, so the surface area formula of a sphere is 4 pi r squared. What we are going to do here is we are going to do the derivative of the surface area with respect to r, meaning we are going to do dSA dr. And on the other side, that means doing power rule. The derivative of 4 pi r squared is 8 pi r. Okay, where do we go from there? Well, look at your given information. Your given information is that the Earth's radius is about 3,959 miles. Okay, so there's an r value. Plus or minus a tenth of a mile, though. What do we do with that information? We don't want to fill that in for r, okay? Where can it go? It can go for dr. It is the possible change in the radius. It's the tolerance of the radius, meaning, this could be off by a tenth of a mile in either direction. And so that we are going to look at as our dr value. So yes, right here, we change dr to 0.1. which I know is weird because there's this thing that like this is not a real thing. This is notation. But yeah, we're not doing a real thing here. We're doing an approximation, so we're going with it, okay? We're going to multiply the 0.1 over to the other side. Sorry if that makes you cringe that I say that. And oops, I forgot to change my R up here to its value. So this calculation approximates the answer to the question posed. What effect would the tolerance of minus a tenth of a mile have on our estimate of the Earth's surface area? If we do this calculation, which I'm definitely going to grab a calculator for, and I am going to multiply with the pi in there. The approximation of the Earth's surface area could be off by this amount, 9,950.05 to square miles. Throw that minus back in there, and you got yourself an answer. And again, what we just found was an approximation of a change of one variable by looking at a small change in another variable, and that's called differentials. Now, understanding differentials leads us to one other application that I absolutely love called related rates. But before we get there, I do want to remind you that earlier this year, we have talked about looking at derivatives with rates of change, like velocity, acceleration, jerk. Does that all sound familiar? Okay, and remember this one? I even had like a really fun little prop in this video. Maybe you didn't see it. Maybe you should see it. Remember this? By the way, his name's Jerry Springer. Is this weird? It's Jerry Springer. Okay, anyway, you see how you see how fun derivatives can be? Look at that. I have props all over the place for this class. I'm not trying to sell it or anything. Okay, anyway, we did talk about derivatives in the context of looking at them as rates of change, but those were functions that were explicitly written in terms of time. You would start with like maybe a position function that was written in terms of time and take the derivative, and there's your velocity function in terms of time, and so on. Okay, what we are going to look at here are equations that are not explicitly written in terms of time. However, you can differentiate them with respect to time, and what you get out of that is an equation that relates all of the rates of those variables. Okay, so let's start with a really simple example. If you have a ladder leaning against a wall, and that ladder starts to slide down the wall, okay, do you realize that the top of the ladder is not sliding at the same rate as the bottom of the ladder? The top of the ladder going down the wall is not changing at the same rate as the bottom of the ladder going across the floor. And what I really mean by that is that this distance is not changing at the same rate as this distance. Okay, that's what I'm saying here. And it's because of the relationship between these values in the Pythagorean theorem. Now, that might not be the most exciting example. So instead of actually going through any specifics with that example, let's look at this one. Okay, this is one of my favorite problems that I do all year in AP Calculus, and it is a related rates problem. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 of a mile north of the intersection and the car is 0.8 of a mile to the east, the police determine with radar that the distance between them and the car is increasing at a rate of 20 miles per hour. Okay, if the cruiser is moving at 60 miles per hour at the instant of the measurement, what is the speed of the car? All right, so I admit this problem is a little bit contrived. The police are determining with radar the distance between them and how that's changing, not just the speed of the car. Okay, I get it. But still, this problem is fun. And usually what I have my students do is I have them draw a picture of the situation. We have a police cruiser. There's my police cruiser. It's a rectangle. You know, math teachers are not artists, right? It's approaching from the north, a right-angled intersection. Okay, so it's going this way. And the speeding car has turned and is moving east in this direction. There it is. It's going that way. That's supposed to be a right angle there. Okay, the police determined that this distance is changing at a rate of 20 miles per hour. So what we have here is a right triangle. We could call this side A, we could call this side B, we could call this side C, and the formula that we're going to set up here to use is the Pythagorean theorem to relate all of the variables that are changing. And when we differentiate the Pythagorean theorem, we are going to have a formula that relates the rates of change. So what you need to keep in mind when you're doing a derivative of a formula like this is that everything is with respect to time. All of your rates are with respect to time. And so you need to use implicit differentiation here. The derivative of a squared is 2a dA over dt. The derivative of b squared is 2b dB over dt. The derivative of c squared is 2c dc over dt. And then you have the really fun part where you get to fill in all of the information. And I usually, talk about that briefly with my students and then have them do it. For example, we know that at this moment in time, A is 0.6, B is 0.8. We don't have a C value, but could we easily know what the C value is? Yes, if we just go back to the original form of the Pythagorean theorem, filling in 0.6 for A and 0.8 for B, or just using a Pythagorean triple here, we can easily find that C is equal to 1 mile. And we're given one other value. That distance, that C distance, is changing at 20 miles per hour. And usually my students figure out pretty easily that that is the dc. This right here is the dc over dt value. Oh, we have another number too. I'm sorry. The police cruiser itself is moving at 60 miles per hour, and that is the dA over dt value. So filling in all of that information, you then find that you only have one variable left. Okay, I'm sorry. My mind was just going nuts because I was running out of room, and actually I didn't have it set up the way that I typically like to have them set up. So I paused it, I fixed it, and I'm back. Okay, so here is all of our information, and what I typically like to do is put a box around what variable are we trying to find and note that, and that is dB over dt. That is the variable that represents the speed of the car that is being chased. Again, we relate the variables with the Pythagorean theorem. We differentiate it with respect to time, and that means multiplying by a d, whatever variable dt, you're working with, anytime you're deriving a variable that's not time. And finally, we fill in our information to then solve for the unknown variable. Now, this is the point where my students solve and they get an answer that makes absolutely no sense. And I ask them, Why? Why does it not make sense? And usually a lot of them get very angry with me and they feel like they did garbage work and they try to erase it all. And I tell them, no, don't do that. There's one little thing that you need to keep in mind, and that is the direction of the change, right? If this cursor is moving toward the intersection, that means that the value of A is decreasing. And so you need to interpret that rate as negative. We need to look at this 60 miles per hour as negative. And just throwing that little negative in place right there will save the day, and we will calculate the value of the speed of the speeding car to be 70 miles per hour. 70 miles per hour is a car that is being chased. Okay. Kind of sounds like the O.J. Simpson chase, doesn't it? Actually, I think they were going slower than that. I usually like to show this YouTube video whenever we start this section. I show like the footage of the O.J. Simpson car chase, and I talked to them about, as a little girl, I watched that live on TV, and it was like the most interesting thing I had seen as a 8 or 9-year-old, however old I was at the time, I don't know. Okay, but that is an example again of what we call related rates, and I do believe that that was the last thing on our list to discuss, yes, for our applications of derivatives. So I will leave you with a meme that I made to sort of sum up how you might feel about derivative applications as you study the unit. As a calculus student, you need to know your derivative rules. There will be times where you have to remember formulas. There's lots of algebra. Units become very important. And understanding that a derivative is slope, but all of the applications that you can apply with slope is important. You're going to see problems in words with multiple steps. And of course, any student always has to deal with those burnouts and distractions as well. So I wish you luck in your study of derivative applications. I hope my rambling in this video was at least a little bit helpful to get you interested in the topic, or at least to let you know what you are about to embark on. Bye.